So here's something that might seem a little strange to think about right now, lying there in the dark. But just stay with me for a second. Right now, at this exact moment, there are invisible fields passing through your body, through the walls of your room, through the pillow under your head. They're threading through the planet beneath you and radiating outward from the star that's currently on the other side of the Earth. These fields are holding your atoms together, carrying the signal to whatever device is playing my voice, and gently aligning the needle of every compass on the planet so it points roughly north. And the wild thing, the really wild thing, is that for almost all of human history, nobody had the faintest idea any of this was happening. Electromagnetism. It's one of those words that sounds immediately intimidating, like it belongs in a textbook you'd rather not open. But here's what I want you to know before we go any further. Electromagnetism is not some abstract, unreachable thing. It is the force that governs nearly everything you experience in the moment you wake up to the moment you fall asleep. The light you see by, the touch you feel, the chemistry that keeps you alive, the technology that surrounds you, all of it, every bit of it, is electromagnetism at work. Gravity gets all the fame, and sure, gravity is important. It keeps you from floating off into space. But electromagnetism is the one doing the real heavy lifting in your daily life. It's the reason solid objects feel solid. It's the reason your hand doesn't pass through the mattress. It's the reason a sunset has color. And tonight, we're going to walk through it. Slowly. Gently. From the very beginning, from a time when people thought lightning was the anger of gods and a strange yellow stone from the shores of the Baltic Sea was somehow alive because it could pick up feathers. We're going to follow the thread of human curiosity as it slowly, painstakingly, over centuries, unraveled one of the deepest truths about the universe. And if you drift off somewhere along the way, that's perfectly fine. That's kind of the point. Let the ideas wash over you. Some of them will stick. Some of them will become part of a dream. Either way, we're in no hurry. Let's start where it all started, which is honestly a little hard to pin down because people have been noticing electrical and magnetic phenomena for a very, very long time without understanding them. But if you want a beginning, a real beginning, you could do worse than ancient Greece, somewhere around 600 BCE, in a coastal town called Miletus. Miletus was one of those remarkable places that the ancient world occasionally produced, a trading hub on the western coast of what's now Turkey, where goods and ideas flowed in from Egypt, Mesopotamia, and all across the Mediterranean. And living there was a man named Thales. Thales of Miletus. He's sometimes called the first philosopher, and while that's probably an exaggeration, he was undeniably one of the earliest people in the Western tradition to look at natural phenomena and say, essentially, I bet there's a non-magical explanation for this. He was interested in everything: geometry, astronomy, the nature of water, and at some point, he noticed something peculiar about amber. Amber, if you haven't held a piece, is fossilized tree resin. It's lightweight, warm to the touch, and it has this beautiful golden translucence. The Greeks called it electron, which is where we eventually get the word electricity. And what Thales noticed, or at least what's attributed to him, is that if you took a piece of amber and rubbed it against fur or wool, it would suddenly attract small, light objects, bits of straw, feathers, dust. It was as if the amber had come alive, reaching out with an invisible hand to grab things nearby. Now, think about what that must have looked like to someone in the 6th century BCE. You rub a pretty stone on your cloak, and suddenly it can move things without touching them. That's genuinely eerie. There's no visible mechanism, no string, no lever, no wind, just this silent, invisible pull. Thales reportedly concluded that amber must have a soul, that it was, in some sense, alive. And honestly, given what he had to work with, that's not a terrible hypothesis. He was wrong, of course, but he was wrong in an interesting way. He recognized that something real was happening, something that demanded an explanation, and he reached for the best framework he had. Around the same time, and possibly even earlier, people in various parts of the world were also noticing something strange about certain rocks. Specifically, there were stones found near the ancient city of Magnesia, again in what's now Turkey, that could attract pieces of iron. These were what we'd now call lodestones, naturally magnetized chunks of the mineral magnetite. And just like amber's trick with feathers, this was deeply mysterious. A rock that grabs iron, no rubbing required, no preparation. Just bring a piece of iron close enough, and the stone pulls it in. The word magnet comes directly from Magnesia, from those stones found in that region. And for centuries, that's essentially where things stood. People knew about two weird invisible forces, the amber force and the lodestone force, and they had no idea that these two phenomena were related. Why would they? One required rubbing and worked on straw. The other was permanent and worked on iron. They seemed like completely different things. And in a sense, that's the central mystery that would take over 2,000 years to solve. The realization that electricity and magnetism are not two separate forces, but two faces of the same underlying phenomenon. But we're getting ahead of ourselves. Let's stay in the ancient world for a moment longer, because there's something important happening here that's easy to overlook. The Greeks and the Chinese, who independently discovered magnetic compass effects, were observing real physics. Real, fundamental physics, the same physics that powers the electric motor in an elevator and the MRI machine in a hospital. They just didn't have the tools, the mathematics, or the conceptual framework to make sense of what they were seeing. And that gap between observing a phenomenon and actually understanding it is one of the great recurring themes in the history of science. Sometimes that gap lasts decades. In the case of electromagnetism, it lasted millennia. So for a very long time, roughly from Thales, all the way through the Roman period and deep into the Middle Ages, not much progress was made on understanding either electricity or magnetism in any fundamental way. People used lodestones. The Chinese developed the magnetic compass, probably sometime around the 1st or 2nd century CE, which was a staggeringly important practical invention. It made reliable navigation possible, which changed trade, exploration, warfare, everything. But nobody could explain why a compass needle pointed north. They just knew it did, and they used it. Which, honestly, is very human. We're remarkably good at using things we don't understand. The real story of electromagnetism as a science, as opposed to a collection of curiosities, doesn't really begin until the late 1500s. And it begins with a man who deserves to be far more famous than he is. His name was William Gilbert, and he was the personal physician to Queen Elizabeth I of England. Now, Gilbert was a doctor by profession, and apparently a very good one. You don't become the Queen's physician by being mediocre. But his real passion, the thing that consumed his evenings and weekends and probably kept him up at night, was magnetism. He was obsessed with it. And in the year 1600, he published a book called De Magnete, On the Magnet, that is genuinely one of the most important scientific works of its era. It's a book that doesn't get nearly enough credit. Here's what Gilbert did that was so remarkable. First, he actually did experiments. That sounds obvious now, but in 1600, the dominant approach to understanding nature was still largely Aristotelian. You reasoned about things from first principles, you cited ancient authorities, you argued logically. Actually, getting your hands dirty and testing things systematically was not the default mode. Gilbert did hundreds of experiments. He tested which materials could be magnetized. He tested whether magnets worked through barriers. He carved a lodestone into a sphere. He called it a terrella, a little earth, and showed that a compass needle placed near it behaved exactly the way real compasses behave on the surface of the real earth. And from this, he made an extraordinary leap. He proposed that the earth itself was a giant magnet. That's why compasses point north. Not because of some mystical force from the pole star, not because of magnetic mountains at the edge of the world, which were actual theories people held. No, the planet itself is magnetic. The whole thing. Think about what a bold claim that was in 1600. He was saying that the ground beneath your feet, the entire globe, has the same property as this strange little rock from Magnesia. And he was right. We now know that Earth's magnetic field is generated by convection currents in the planet's liquid iron outer core, a kind of natural dynamo. But Gilbert didn't know that mechanism. He just knew, from his terrella experiments, that a spherical magnet reproduced the behavior of Earth's compass effects perfectly. That's beautiful, careful, experimental reasoning. Gilbert also did something else that's crucial for our story. He drew a clear distinction between the Ampère effect, what he called the electric force, coining the term from the Greek electron, and the magnetic force. He recognized that they behaved differently. The electric force required rubbing, was temporary, worked on many materials, and could be blocked by placing a sheet of paper between the amber and the straw. The magnetic force was permanent, worked primarily on iron, and couldn't be blocked by interposing non-magnetic materials. So Gilbert actually pushed the two phenomena further apart in people's minds. He said, essentially, these are different things. Stop confusing them. And here's the thing. He wasn't wrong exactly. They do behave differently in many observable ways. But the deeper truth, the truth that wouldn't emerge for another 200 years, is that they're intimately connected. They're aspects of a single, unified force. Gilbert couldn't have known that. He was working with what he could see and measure, and what he could see and measure told him they were separate. So he drew a line between them, and that line would persist in scientific thinking for a very long time. After Gilbert, the study of electricity in particular started to pick up speed, partly because it was just so much fun to play with. I mean that literally. In the 1600s and 1700s, electrical experiments became a form of entertainment. People discovered that you could generate static electricity by spinning a glass globe against your hand, and that the sparks and attractions you could produce were genuinely spectacular. There were traveling showmen who would set up demonstrations in town squares. They'd suspend a boy from silk ropes, charge him up with a friction machine, and then have audience members approach his face, drawing sparks from his nose. People loved it. It was the closest thing to magic that the Enlightenment had to offer. But behind the showmanship, some genuinely important work was being done. In 1745, a Dutch scientist named Peter van Musschenbroek, working at the University of Leiden, accidentally invented something that changed everything. He was trying to store electrical charge in a jar of water, and he got a shock so violent that he reportedly said he wouldn't repeat the experiment for the entire Kingdom of France. What he'd created was the Leyden jar, essentially the first capacitor, the first device that could store a significant amount of electrical charge and release it all at once. Suddenly, you could bottle lightning. You could accumulate charge over time and then discharge it in a single dramatic spark. The Leyden jar turned electricity from a curiosity into something you could actually work with, something you could experiment on in a controlled way. And it attracted the attention of one of the most remarkable minds of the 18th century, a man who was already famous as a printer, a writer, a diplomat, and a political philosopher. A man who, in the middle of an extraordinarily busy life, somehow found time to conduct some of the most important electrical experiments of his era, and who very nearly killed himself doing it. His name was Benjamin Franklin, and what he figured out about the nature of electrical charge would lay the groundwork for everything that came after. Franklin was already in his 40s when he got interested in electricity, which is worth pausing on for a moment. This wasn't some young university researcher with nothing else on his plate. By the time a friend sent him some glass tubes and instructions for performing electrical experiments in 1743, Franklin had already retired from the printing business, had already published Poor Richard's Almanac, had already helped found the American Philosophical Society. He was wealthy, respected, and could have spent the rest of his life comfortably doing nothing at all. But something about electricity grabbed him. He became, by his own account, completely obsessed. He wrote to a friend that he had little leisure for anything else. And here's what made Franklin different from a lot of the people playing with electricity at the time. He wasn't interested in the spectacle. He wanted to understand what was actually happening. What was this stuff? What was it made of? Why did it behave the way it did? And he brought to the problem something that a lot of natural philosophers of his era lacked: a deeply practical mind. Franklin was a craftsman, a tinkerer, a man who thought with his hands as much as his head. He didn't just want to describe electricity. He wanted to build a model of it that made sense. So here's what Franklin proposed, and it was genuinely revolutionary. He said that electricity was a single fluid, not two different fluids, which was the competing theory at the time. A single fluid that existed in all matter. When an object had more than its normal share of this fluid, Franklin called it positively charged. When it had less than its normal share, he called it negatively charged. And the key insight, the really beautiful part, was this: electrical phenomena weren't about creating charge. They were about moving it. When you rubbed a glass rod with a silk cloth, you weren't generating electricity from nothing. You were transferring this fluid from one object to another. The total amount stayed the same. What one object gained, the other lost. Think about what that means. Franklin was articulating, in 1747, what we now call the conservation of charge, one of the most fundamental principles in all of physics. He didn't have the mathematics to express it formally, and he didn't know about electrons, which wouldn't be discovered for another 150 years. But the core idea was right. Charge is conserved. It's never created or destroyed, only moved around, and we still use his convention today: positive and negative, plus and minus. Every time you see a plus sign on a battery terminal, that's Franklin's language. Every time an electrical engineer talks about conventional current flowing from positive to negative, that's Franklin's framework, still in use nearly 3 centuries later. Now, there's a famous irony here that's worth mentioning. Franklin guessed wrong about which direction the fluid actually flowed. He assumed the electrical fluid moved from the positively charged object to the negatively charged one. We now know that what's actually moving, the electrons, flow the other way, from negative to positive. But by the time anyone figured that out, Franklin's convention was so deeply embedded in science and engineering that nobody wanted to change it. So we just kept it. which is why, to this day, conventional current flows in the opposite direction from actual electron flow, and every first-year electrical engineering student has to wrap their head around that slightly maddening contradiction. You can thank Ben Franklin for that particular headache. But let's talk about the experiment everyone knows, or thinks they know. The kite. June 1752. Philadelphia. A thunderstorm rolling in. The story, as most people tell it, goes something like this. Franklin flew a kite into a thunderstorm with a metal key attached to the string. Lightning struck the kite. Electricity traveled down the string to the key. And Franklin proved that lightning was electrical. It's one of the most famous experiments in the history of science. And almost every detail of that popular version is slightly wrong. Here's what actually happened, as best as historians can reconstruct it. Franklin did fly a kite during a thunderstorm, yes. But the kite was not struck by lightning. If it had been, Franklin would almost certainly have been killed. What he was doing was much more subtle and, honestly, much more clever. He flew the kite up into the charged atmosphere of a thunderstorm, and the kite and its string gradually accumulated electrical charge from the surrounding air. The key was tied to the string near the bottom, and Franklin noticed the loose fibers of the string standing on end, repelling each other the way charged objects do. When he brought his knuckle near the key, he got a spark. A small spark, not a massive bolt. And he was able to use that spark to charge a Leyden jar, proving that the charge collected from the storm clouds was the same stuff, behaved in exactly the same way as the charge produced by rubbing glass in a laboratory. That was the real breakthrough. Not that lightning was dramatic or powerful. Everyone already knew that. The breakthrough was that lightning and the little sparks you could make with a friction machine were the same phenomenon, just at wildly different scales. The heavens and the laboratory were playing by the same rules. And that idea, that natural phenomena and human-scale experiments obey the same laws, that's one of the most important principles in all of science. Franklin demonstrated it with elegance and, frankly, with extraordinary personal courage, because even the indirect charge he was collecting could have been dangerous. And here's the practical payoff, the thing that made Franklin a celebrity across all of Europe, the lightning rod. If lightning is electrical, and if electrical charge can be conducted safely through metal, then you can protect buildings by putting a pointed metal rod on the roof connected to a wire running down into the ground. The charge gets conducted harmlessly into the earth instead of setting the building on fire. It was so simple, so elegant, and so immediately useful that it spread across the world within years. Churches, which had always been particularly vulnerable because of their tall steeples, started putting up lightning rods. Ships installed them. Public buildings, private homes. Suddenly, one of the most terrifying and destructive forces in nature could be tamed with a piece of iron and some wire. Franklin refused to patent the invention. He believed it should be freely available to everyone. That tells you something about the man. So by the middle of the 18th century, thanks to Franklin and others, people had a reasonable working understanding of static electricity. They knew charge could be positive or negative. They knew it could be stored in Leyden jars. They knew it was conserved. They knew it was related to lightning. They could produce it, accumulate it, discharge it. But there was still a massive gap in understanding, and it had to do with something that seems obvious to us now but was genuinely puzzling at the time. All of this electricity was static. It was charge that built up and then discharged in a single dramatic spark. What nobody had figured out yet was how to make electricity flow continuously, a steady current, a river of charge instead of a sudden flood. That was the missing piece, and it would take a dead frog to find it. The year is 1780, and we're in Bologna, Italy. Luigi Galvani is a professor of anatomy at the university, and he's dissecting frogs. This is perfectly normal. Galvani is an anatomist, and frogs are standard laboratory subjects. But on this particular day, something strange happens. One of Galvani's assistants touches a metal scalpel to the sciatic nerve of a dead frog's leg, and the leg twitches. It kicks as if the frog were alive. Now, there was an electrostatic machine running in the same room at the time, and Galvani noticed that the twitching seemed to happen when the machine sparked. He was intrigued. He started experimenting systematically, and over the next several years, he discovered that he could make the frog legs twitch by touching them with two different metals, say, copper and iron, connected together. No friction machine needed, no Leyden jar, just two different metals and a dead frog. Galvani concluded that the electricity was coming from the frog itself. That animal tissue contained its own form of electricity, which he called animal electricity. He published his findings in 1791, and they caused a sensation. The idea that living things contained their own electrical fluid was thrilling, almost mystical. It suggested that electricity was somehow connected to the life force itself, and it captured the public imagination in ways that would echo for decades, most famously in Mary Shelley's Frankenstein, published in 1818, where a dead body is reanimated by electrical means. That novel was directly inspired by the Galvani experiments and the public demonstrations that followed them, where showmen would make dead animals and even human corpses twitch and grimace by applying electrical current. The boundary between electricity and life seemed for a moment terrifyingly thin. But not everyone was convinced by Galvani's explanation. About 100 miles away, at the University of Pavia, another Italian scientist was reading Galvani's papers with great interest and growing skepticism. His name was Alessandro Volta, and he thought Galvani had the story exactly backward. Volta believed the electricity wasn't coming from the frog at all. The frog was just a detector. A very sensitive one, but still just a detector. The real source of electricity, Volta argued, was the junction between the two different metals. The frog's leg twitched not because it contained animal electricity, but because the contact between copper and iron generated a flow of charge that stimulated the nerve. This set off one of the great scientific rivalries of the era. Galvani and Volta argued back and forth, each conducting experiments designed to prove the other wrong. And the beautiful thing about this rivalry is that they were both partly right. Galvani was correct that biological tissue does generate its own electrical signals. Your nervous system runs on electricity. Your heart beats because of electrical impulses. And the study of bioelectricity is a thriving field today. But Volta was right about the specific phenomenon they were arguing over. The twitching was caused by the metals, not the frog, and Volta proved it in the most dramatic way possible. In 1800, he built a device that produced a steady, continuous flow of electrical current with no frog anywhere in sight. He stacked alternating discs of zinc and copper, separated by pieces of cardboard soaked in salt water, and connected the top and bottom of the stack with a wire. And from that wire flowed a steady, reliable current of electricity. Not a spark, not a momentary jolt, a continuous flow like a river instead of a raindrop. And that changes everything. Think about what that means. Before Volta's pile, every electrical experiment was basically a one-shot deal. You'd charge up a Leyden jar, discharge it, get a spark, and then you'd have to start over. It was like trying to study water by throwing individual cups of it against a wall. You could learn a few things, sure, but you couldn't really observe how water behaves when it flows. You couldn't run a mill. You couldn't irrigate a field. You were stuck with splashes. Volta's pile gave scientists a faucet, and the moment they had a faucet, a continuous, controllable source of electrical current, the entire pace of discovery changed. Within weeks of Volta's announcement, scientists across Europe were building their own piles and doing things with electricity that had been simply impossible before. One of the first and most dramatic demonstrations came from two English chemists, William Nicholson and Anthony Carlisle, in the spring of 1800. They built their own voltaic pile, ran wires from it into a container of water, and watched as bubbles appeared at each wire. At one wire they got hydrogen gas, at the other, oxygen. They had split water into its component elements using nothing but electricity. This was electrolysis, and it was a revelation. It meant that electrical force was somehow involved in the chemical bonds holding molecules together. Electricity wasn't just a curiosity of amber and sparks. It was woven into the very structure of matter. And here's the thing. Volta himself didn't fully understand why his pile worked. He thought the electricity was generated purely by the contact between the two metals, that the wet cardboard was just there to prevent the disks from short-circuiting. He didn't realize that the chemical reaction between the metals and the salt solution was actually what produced the current. It took decades for scientists to work out the full electrochemistry of batteries. But that's often how it goes in science and engineering. Someone builds a thing that works, and then other people spend years figuring out why it works. The doing comes before the understanding. Now, I want you to hold on to that image of Volta's pile, those stacked disks, that steady current flowing through a wire, because what happens next is one of the most important moments in the entire history of physics, and it happens almost by accident. We're in Copenhagen now. It's the spring of 1820, and a Danish physicist named Hans Christian Ørsted is giving a lecture to students. Ørsted had been thinking for years about whether there might be some connection between electricity and magnetism. This was a deeply unfashionable idea. Most scientists at the time treated electricity and magnetism as completely separate phenomena. Yes, they were both invisible forces. Yes, they could both attract and repel, but they seemed to operate by different rules, on different materials, in different ways. Magnets attracted iron. Electricity flowed through wires. What could they possibly have to do with each other? But Ørsted had a philosophical hunch, influenced, interestingly, by the German Romantic tradition of Naturphilosophie, which held that the forces of nature must be fundamentally unified. He felt, almost on an aesthetic level, that electricity and magnetism had to be related somehow. And during that lecture in April of 1820, he set up a demonstration. He placed a compass needle near a wire that was connected to a voltaic battery. And when he closed the circuit, when current began flowing through the wire, the compass needle moved. Let that sink in for a moment. A compass needle, which responds to magnetic force, was deflected by an electric current flowing through a nearby wire. Electricity had produced magnetism. Not static electricity sitting on a charged object, but moving electricity, current flowing through a conductor. The current created a magnetic field around the wire, and that field pushed the compass needle. Now, Ørsted's exact experience during that lecture is a matter of some historical debate. Some accounts say he noticed the effect for the first time right there in front of his students, that it was a genuine moment of surprise. Others suggest he had seen hints of it before and set up the demonstration hoping to confirm his suspicion. Either way, what matters is what he did next. He spent the summer of 1820 carefully experimenting, mapping out the behavior of the compass needle around the current-carrying wire, and in July he published a short paper, written in Latin, as was still common for scientific announcements, describing his discovery. And here's what's really fascinating about what Ørsted found. The magnetic force around the wire didn't behave the way anyone expected. If you hold a magnet near a compass, the needle points toward the magnet. The force acts along the line between them, pulling or pushing directly. That's intuitive. That's how gravity works too. Forces act along the line connecting two objects, but the magnetic force around a current-carrying wire doesn't do that. The compass needle doesn't point toward the wire or away from it. Instead, it points around the wire, in a circle. If you imagine the wire running vertically, the magnetic force wraps around it in horizontal loops, like invisible rings stacked along the wire's length. This was deeply strange. No one had ever encountered a force that acted in circles before. Every force anyone knew about, gravity, the electric force between charges, the force of a spring, acted in straight lines. Push, pull, attract, repel, all along a direct path between two objects. But magnetism from a current said no. I'm going to curl around this wire in circles, and if you don't like it, that's your problem. This circular pattern would later turn out to be one of the most important clues about the deep geometry of electromagnetism. But in 1820, it was just baffling and wonderful. News of Ørsted's discovery spread across Europe like wildfire, and one of the people it hit hardest was a French physicist and mathematician named André-Marie Ampère. Ampère heard about Ørsted's experiment in September of 1820, and within a week, a single week, he had begun developing a comprehensive mathematical theory of how electric currents produce magnetic forces. Ampère was a remarkable person, and his story is worth lingering on for a moment. He'd had a difficult life. His father was executed during the French Revolution, guillotined during the Terror in Lyon, when Ampère was just 18 years old. The trauma affected him deeply, and by some accounts, he spent over a year in a state of near catatonic grief. He eventually recovered, threw himself into mathematics and science, and became one of the most brilliant minds in France. But he carried a kind of melancholy with him throughout his life. His personal relationships were often troubled. His first wife died young. His second marriage was unhappy. He poured himself into his work with an intensity that seemed at times like it was the only thing holding him together. And when Ørsted's discovery reached him, something ignited. In the span of just a few months in late 1820 and early 1821, Ampère conducted a series of experiments and mathematical analyses that laid the foundation for an entirely new branch of physics. He showed that two parallel wires carrying electric currents exert forces on each other. If the currents flow in the same direction, the wires attract. If they flow in opposite directions, the wires repel. Think about that. Two wires, carrying nothing but flowing charge, pulling toward each other or pushing apart, with no magnets anywhere in sight. This was magnetism being created purely by electricity in motion. Ampère went further. He proposed that all magnetism, not just the magnetism around wires, but the magnetism of permanent magnets, of lodestones, of compass needles, was ultimately caused by tiny circular electric currents flowing within the material. Inside a piece of iron that's been magnetized, he suggested, there are countless microscopic loops of current, all aligned in the same direction, and their combined effect produces the magnetic field we observe. This was an extraordinary leap of imagination. He was saying that magnetism isn't a separate force at all. It's just what electricity does when it moves. And here's the kicker. He was essentially right. We now know that the magnetism of permanent magnets comes from the motion of electrons within atoms. Not circular currents in the way Ampère imagined exactly, but the orbital motion and spin of electrons, which do behave like tiny current loops. The unit of electric current, the ampere, is named after him, and it's the unit you see on every circuit breaker in your house, on every fuse, on every power supply. Every time you flip a switch and a label says 15 amps or 20 amps, that's André-Marie Ampère's name, the grief-stricken genius who decoded the relationship between current and magnetic force in a few feverish months. So by the end of 1820, the world of physics had been fundamentally altered. Ørsted had shown that electric current produces magnetism. Ampère had shown that currents exert magnetic forces on each other, and proposed that all magnetism is really just electricity in motion. The wall between electricity and magnetism had been breached. But here's the question that was now hanging in the air. The obvious question that you might already be asking. If electricity can produce magnetism, can magnetism produce electricity? Is the relationship symmetrical? Can you take a magnet, do something with it, and get an electric current to flow? This is one of those questions that seems simple once you ask it, but answering it took over a decade. And the person who finally cracked it was someone we need to spend real time with, because he's one of the most extraordinary figures in the entire history of science. He had almost no formal education. He couldn't do advanced mathematics. He came from poverty, apprenticed to a bookbinder as a teenager, and taught himself science by reading the books he was supposed to be binding. His name was Michael Faraday, and what he discovered in a small basement laboratory at the Royal Institution in London would make the modern world possible. Faraday was born in 1791 in Newington Butts, a rough neighborhood in South London. His father was a blacksmith who was frequently ill and couldn't always provide for the family. Faraday's formal schooling was minimal. He learned to read and write and do basic arithmetic, and that was about it. At 14, he was apprenticed to a bookbinder named George Rebow, and this turned out to be one of those accidents of fate that changes history. Because Faraday didn't just bind the books, he read them. He read everything that came through the shop, but he was particularly captivated by an entry on electricity in the Encyclopedia Britannica, and by a book called Conversations on Chemistry by Jane Marcet. These books lit a fire in him. He started attending public science lectures whenever he could, taking meticulous notes, binding those notes into little books of his own. And then, in 1812, a customer at the bookshop gave young Faraday tickets to a series of lectures at the Royal Institution delivered by the most famous scientist in England, Sir Humphry Davy. Faraday attended all 4 lectures, took detailed notes, bound them beautifully, and sent them to Davy with a letter asking for a job. Davy was impressed, and in 1813, he hired Faraday as a laboratory assistant. It was the beginning of one of the most productive scientific careers in history. And it started because a 21-year-old bookbinder's apprentice had the nerve to send a bound notebook to a famous chemist and say, essentially, "Please let me work for you." Faraday spent years learning the craft of experimental science under Davy. He traveled across Europe with Davy, met other scientists, absorbed everything he could. And by the early 1820s, when news of Ørsted's and Ampère's discoveries reached England, Faraday was ready. He was already a skilled experimenter with a deep intuitive feel for how physical forces behave. And he became obsessed with the relationship between electricity and magnetism. In 1821, Faraday built a device that demonstrated something beautiful and strange. He suspended a wire so that it could rotate freely around a fixed magnet, and when he passed current through the wire, it began to spin, continuously revolving around the magnet in a circle. This was the first electric motor. It was crude, it was simple, it couldn't do any useful work, but it demonstrated the principle. A current-carrying wire in a magnetic field experiences a force, and if you arrange the geometry correctly, that force can produce continuous rotation. Every electric motor on Earth, from the one spinning your refrigerator compressor right now, to the ones in electric cars, to the tiny vibration motor in your phone, is a descendant of that little spinning wire in Faraday's lab. But Faraday wanted more. He wanted to reverse the trick. If current flowing through a wire could make it move in the presence of a magnet, could moving a wire in the presence of a magnet make current flow? He tried, and for 10 years, he mostly failed. He would set up a magnet near a wire connected to a meter and just wait. Nothing. No current. The magnet sat there, the wire sat there, and nothing happened. It was maddening, because the symmetry seemed so obvious. Electricity makes magnetism, so magnetism should make electricity. But it wouldn't cooperate. And then, on August 29, 1831, Faraday finally understood what he'd been missing, and the answer was so elegant, so beautifully simple, that it almost seems too good to be true. The answer was change. Not the presence of a magnet, not the strength of the magnet, not how close the wire was to the magnet. Change, movement, variation over time. That was the missing ingredient, and once you see it, you can never unsee it. Here's what happened. Faraday wound 2 separate coils of wire around an iron ring. Think of it like a donut made of iron, with wire wrapped around one side and a different wire wrapped around the other side. The 2 coils weren't connected to each other at all. One coil was hooked up to a battery. The other was connected to a galvanometer, which is just a sensitive device for detecting tiny currents. And when Faraday closed the switch to send current through the first coil, something happened in the second coil. The galvanometer needle twitched, just for a moment. A little flicker, and then nothing. The current was still flowing through the first coil. The magnetic field was still there, but the galvanometer went dead, sat there like a stone. And then, and this is the beautiful part, when Faraday opened the switch and cut the current off, the galvanometer twitched again, but this time in the opposite direction. Another momentary flicker, and then silence. Think about what that means. It wasn't the magnetic field that produced the current in the second coil. It was the appearance and disappearance of the magnetic field. The change, the moment of transition. While the field was steady, nothing. While the field was growing or collapsing, a pulse of electricity. Faraday had discovered electromagnetic induction, and it is, without exaggeration, one of the most important discoveries in the entire history of human civilization. Because what he'd found was the principle that lets you turn motion into electricity, and that changes everything. Let me say that again, because it's worth sitting with. A changing magnetic field creates an electric current, not a static one, a changing one. If you move a magnet toward a coil of wire, current flows. If you hold the magnet still, current stops. If you pull the magnet away, current flows again, but in the opposite direction. The faster you change the field, the more current you get. This is the principle behind every electrical generator ever built. Every power plant on Earth, coal, gas, nuclear, hydro, wind, they all work the same way at the most fundamental level. They take some source of energy, use it to spin a magnet inside coils of wire, and the changing magnetic field induces current in those coils. That current is what flows through the wires to your house. When you flip a light switch, you are completing a circuit that stretches all the way back to some coil of wire spinning in a magnetic field somewhere, right now, as you listen to this. Faraday didn't express his discovery in mathematical equations. He wasn't that kind of thinker. Instead, he developed a way of visualizing what was happening that turned out to be profoundly important. Maybe even more important than the discovery of induction itself, in the long run. He imagined what he called lines of force. Picture a bar magnet sitting on a table. If you sprinkle iron filings around it, and you've probably seen pictures of this, the filings arrange themselves into these beautiful curved lines arcing from one pole of the magnet to the other. Faraday looked at those patterns and said, essentially, those lines are real. They're not just a pretty picture. They represent something physical. The space around the magnet is filled with these lines of force, and they have properties. They're under tension, like stretched rubber bands trying to shorten themselves. And they repel each other sideways, like parallel hoses trying to push apart. The magnetic field, for Faraday, wasn't just a mathematical abstraction. It was a physical thing that filled space, that had structure, that stored energy. Now, this might sound obvious to you, because we've all grown up with the idea of fields. But in Faraday's time, this was radical. The dominant way of thinking about forces, going all the way back to Newton, was action at a distance. The sun pulls the earth pulls the moon, magnets pull iron, and the force just leaps across empty space instantaneously, with nothing in between. Faraday was saying no, something is in between. The field is in between. The magnet doesn't reach out and grab the iron filing directly. The magnet creates a field in the space around it, and the field is what acts on the iron filing. The force is local. It's mediated by this invisible structure that permeates the space. Most of the mathematical physicists of Faraday's day dismissed this. They thought it was woolly, imprecise, the kind of hand-waving you'd expect from a self-taught man who couldn't write proper equations. And here's where one of the most beautiful intellectual partnerships in the history of science comes in. Even though the two people involved never truly collaborated in person. Because a young Scottish physicist named James Clerk Maxwell read Faraday's papers and saw something that almost everyone else had missed. He saw that Faraday's lines of force weren't just a useful metaphor. They were a deep physical insight that could be made mathematically rigorous. And when Maxwell did that, when he translated Faraday's intuitive pictures into precise mathematical language, the result was one of the greatest achievements in the history of physics. But let's not rush to Maxwell just yet. Let's stay with Faraday a little longer, because his story is so human, and because the way he thought about the world matters. Faraday spent the 1830s and 1840s pushing his discoveries further and further. He showed that induction worked not just with electromagnets, but with permanent magnets too. He built the first dynamo, a copper disc spinning between the poles of a magnet, generating a continuous current. It was feeble, barely enough to detect, but it was the ancestor of every generator in every power station in the world. He discovered that the amount of chemical change produced by electrolysis is directly proportional to the amount of electric charge passed through the solution, Faraday's laws of electrolysis. He invented the terms we still use today: electrode, anode, cathode, ion, electrolyte. He discovered diamagnetism, the fact that almost all materials respond to magnetic fields at least a little, even ones we don't normally think of as magnetic. He showed that magnetic fields affect the polarization of light, which was the first direct evidence that light and magnetism were somehow related. That experiment, done in 1845, was a clue so profound that it would take another 20 years for anyone to fully understand what it meant. And through all of this, Faraday remained an outsider in certain ways. He never held a university position. He was a member of a small, austere Christian sect called the Sandemanians, and his faith was central to his life. He turned down a knighthood. He turned down the presidency of the Royal Society twice. He lived simply. He gave public lectures at the Royal Institution that were legendary for their clarity and showmanship. He was, by all accounts, one of the greatest science communicators who ever lived. His Christmas lectures for children became a tradition that continues to this day. And yet, despite his fame, despite his extraordinary experimental gifts, there was always a faint condescension from the mathematical establishment. Faraday couldn't do calculus. He thought in pictures, in physical intuitions, in the feel of how forces push and pull through space. And the professionals thought that made his ideas somehow less rigorous, less trustworthy. Enter James Clerk Maxwell, born in Edinburgh in 1831, the same year Faraday discovered induction, as it happens. Maxwell was everything Faraday wasn't, socially speaking. He came from a wealthy Scottish family, was educated at Edinburgh and Cambridge, was steeped in mathematics from childhood. He was brilliant in that quiet, almost playful way that some theorists have, where they seem to be having fun with ideas the way other people have fun with puzzles. And from his early 20s, Maxwell was fascinated by Faraday's work. In 1855, when Maxwell was just 24, he published a paper called On Faraday's Lines of Force, and it was a revelation. What Maxwell did was take Faraday's physical picture, those lines of force filling space, under tension, pushing sideways, and show that you could describe them with precise mathematical equations. He used an analogy to fluid flow, imagining the lines of force as tubes through which an incompressible fluid was flowing, and showed that the mathematical structure of such a flow matched the behavior of electric and magnetic fields. It wasn't the final theory. It was a first step, a proof of concept. But it showed that Faraday's intuition could be made rigorous, and it set Maxwell on a path that would consume the next decade of his life. The key insight that Maxwell was building toward, and this took years of work, multiple papers, false starts, and revisions, was that electricity and magnetism aren't just related. They aren't just two phenomena that happen to interact. They are two aspects of a single, unified thing. A single field. A single set of laws. And those laws, when you write them down completely, contain a surprise so stunning that Maxwell himself didn't fully appreciate it at first. Here's the thing Maxwell figured out, and let me try to walk you through it, because it's one of those ideas that seems almost inevitable once you see it, but nobody saw it for decades. Start with what Faraday discovered. A changing magnetic field creates an electric field. That's induction. That's how generators work. Current flows in a wire not because something is pushing charges directly, but because the changing magnetic field creates an electric field, and that electric field is what pushes the charges. Now, there was already a known law going the other direction, Ampere's law, which says that an electric current creates a magnetic field. That's what Ørsted discovered, what Ampère mathematized. So you have this beautiful reciprocity. Changing magnetic fields create electric fields. Electric currents create magnetic fields. But Maxwell noticed something. There was an asymmetry, an inconsistency. Ampere's law, as it was originally written, only worked for steady currents. It didn't account for situations where the electric field was changing over time. And Maxwell realized that if you had a changing electric field, not a current, not charges moving, just an electric field that was growing or shrinking, it should produce a magnetic field, just as a changing magnetic field produces an electric field. He called this the displacement current, and he added it to Ampere's law as a correction term. Now, this might sound like a minor technical fix. A little patch to make the equations consistent. But here's what's wild about it. Once you add that term, once you say that changing electric fields create magnetic fields and changing magnetic fields create electric fields, you get a feedback loop. Imagine an electric field that's oscillating, growing and shrinking. That changing electric field creates a magnetic field. But now that magnetic field is also changing, because it was just created by a changing electric field. And that changing magnetic field creates a new electric field, which changes, creating more magnetic field. And on and on. The fields sustain each other, leapfrogging through space, each one giving birth to the next. Maxwell wrote down the equations for this self-sustaining oscillation, and when he solved them, he found that they described a wave, an electromagnetic wave, a ripple of intertwined electric and magnetic fields propagating through space, requiring no medium, no wire, no material to carry it. Just fields, oscillating in empty space, racing outward from their source. And when Maxwell calculated the speed of this wave, using only the known constants of electricity and magnetism, numbers that had been measured in laboratories with coils and capacitors and had nothing obvious to do with light, the speed came out to roughly 300 million meters per second. The speed of light. Maxwell wrote in a letter to William Thomson in 1861 that the agreement was too close to be a coincidence. Light, he realized, is an electromagnetic wave. The light from the sun, the glow of a candle, the colors of a sunset. All of it is oscillating electric and magnetic fields, racing through space at 300 million meters per second, each field creating the other in an endless, self-sustaining dance. And the same equations that describe light also predict waves at other frequencies, waves that no one had ever detected, waves that were invisible to the eye, but that should, in principle, exist. Maxwell published his complete theory in 1865 in a paper called A Dynamical Theory of the Electromagnetic Field. 4 equations. Just 4. And from those 4 equations, you can derive everything. How charges create electric fields. How currents create magnetic fields. How changing fields create each other. How electromagnetic waves propagate. How light works. How antennas will one day work. How radio, television, radar, Wi-Fi, X-rays, gamma rays, all of it, behaves. 4 equations, and they contain the entire classical theory of electromagnetism. But here's the thing about Maxwell's equations, and this is something that doesn't get talked about enough. When Maxwell published them, almost nobody understood them. The mathematical framework he used was dense, unfamiliar, and frankly kind of a mess by modern standards. He used 20 equations with 20 unknowns, written in a notation that was clunky and hard to work with. The beautiful, compact form of Maxwell's 4 equations that physics students learn today, that came later, cleaned up by Oliver Heaviside in the 1880s. Heaviside was another fascinating character, by the way, a self-taught English engineer who was largely deaf, lived as a recluse, and was so far ahead of his time that the scientific establishment mostly ignored him during his lifetime. He reformulated Maxwell's theory using vector calculus, stripping away the scaffolding to reveal the elegant structure underneath. The four equations we call Maxwell's equations today are really Maxwell's ideas in Heaviside's notation, and even with the theory published, there was a critical question hanging in the air. Maxwell had predicted electromagnetic waves. He'd shown mathematically that they should exist, but nobody had ever detected one. Nobody had ever created one in a laboratory and measured it. Maxwell himself died in 1879 at the age of 48, the same age as his mother when she died of the same cancer. And he never saw his prediction confirmed. He never knew for certain that he was right. That confirmation would come from a German physicist working in a cramped laboratory in Karlsruhe, a man named Heinrich Hertz. And the experiment he designed was one of the most elegant pieces of experimental physics you'll ever hear about. Hertz had studied under Hermann von Helmholtz in Berlin, and Helmholtz had actually suggested the problem to him: find a way to test Maxwell's prediction. Prove or disprove whether electromagnetic waves really exist. And Hertz thought about it for years before he figured out how to do it. The challenge was enormous, if you think about it. You need to generate an electromagnetic wave in one part of a room and then detect it somewhere else without any wires connecting the two. You need to show that something invisible is traveling through empty space, carrying energy from one place to another, and that this something behaves the way Maxwell's equations say it should. That it reflects, refracts, polarizes, and travels at the speed of light. So here's what Hertz built, around 1886 to 1888, in his laboratory at the Technische Hochschule in Karlsruhe. His transmitter was beautifully simple. He took two metal rods, each with a small brass sphere on the end, and arranged them so the spheres were separated by a tiny gap, just a few millimeters. Then he connected this to an induction coil, which is basically a device that takes a low voltage and steps it up to a very high voltage. When the voltage got high enough, a spark would jump across the gap between the two spheres. And here's what's happening during that spark. The electrical charge is oscillating back and forth incredibly rapidly, sloshing from one rod to the other and back again, millions of times per second. And if Maxwell was right, that oscillating charge should be radiating electromagnetic waves outward in all directions, like ripples spreading from a stone dropped in a pond. Now he needed a receiver. And this was even simpler. Just a loop of wire with its own tiny gap. Hertz's idea was that if electromagnetic waves were really spreading through the room, they would hit this loop of wire and induce a tiny oscillating current in it, and that current would produce its own miniature spark across the gap in the receiver. A spark answering a spark, with nothing but empty air between them. And it worked. He saw the tiny spark in his receiver. Across the room, with no wires, no connection, nothing but space between the transmitter and the detector, a spark appeared. Think about that for a second. In a modest laboratory in southern Germany, a 30-year-old physicist had just confirmed one of the most profound predictions in the history of science. Electromagnetic waves were real. They existed. Maxwell had been right. But Hertz didn't stop there, and this is what makes him such a great experimentalist. He went on to show that these waves behaved exactly the way Maxwell's theory predicted. He reflected them off metal sheets and showed they bounced like light off a mirror. He refracted them through prisms made of pitch, a kind of tar, and showed they bent like light through glass. He used a wire grid to polarize them, the same way certain crystals polarize visible light. He measured their wavelength by creating standing waves, reflecting the waves back on themselves and finding the nodes and antinodes, the places where the waves canceled out and where they reinforced. And from the wavelength and the frequency of oscillation, he calculated their speed. It came out to roughly the speed of light. Maxwell had predicted exactly this, that electromagnetic waves would travel at 300 million meters per second, the same speed as light. And here was Hertz, measuring it in his lab. The results were published in 1887 and 1888, and they sent shock waves through the physics community. This was the definitive proof. Electromagnetic waves existed, they traveled at the speed of light, and they obeyed all of Maxwell's predictions. Light itself was an electromagnetic wave, the thing that lets you see, the thing that warms your skin, the thing that carries color and shadow, and the image of every face you've ever loved. It's the same phenomenon as the spark jumping across Hertz's little gap, just at a much, much higher frequency. And here's something poignant about Hertz. When someone asked him what the practical applications of his discovery might be, he reportedly said something like, "It's of no use whatsoever. This is just an experiment that proves Maestro Maxwell was right." He saw it as pure science. He had no idea, couldn't possibly have imagined, that within a decade, people would be using his waves to send messages across oceans. He died young in 1894, at just 36 years old, from a rare blood vessel disease. He never saw radio. He never saw the revolution his work made possible. We honor him every time we talk about frequency. The unit is the Hertz, abbreviated Hertz. Every radio station, every Wi-Fi router, every microwave oven, every cell phone signal. Their frequencies are measured in the unit named after the man who first proved these waves were real. Now, the person who took Hertz's laboratory curiosity and turned it into something the world could use. That's another story entirely, and it's a messy one, full of rival claims and legal battles, and at least one genius who got written out of history for decades. The name most people know is Guglielmo Marconi, the young Italian inventor who, starting in the mid-1890s, figured out how to use electromagnetic waves to send telegraph signals without wires. Wireless telegraphy, they called it. Marconi was 20 years old when he started experimenting on his family's estate near Bologna. And he was brilliant at the practical side, building better antennas, grounding his transmitters, increasing the range step by step. By 1896, he was in England, demonstrating his system to the British Post Office. By 1899, he was sending signals across the English Channel, and in December 1901, he claimed to have received a signal across the Atlantic Ocean from Poldhu in Cornwall to St. John's in Newfoundland, over 2,000 miles of open water. That 1901 transatlantic transmission is actually one of those moments in engineering history where the story is more complicated than the legend. Many physicists at the time believed it shouldn't have been possible. Electromagnetic waves travel in straight lines, and the Earth is curved, so a signal sent from England should shoot off into space long before reaching Newfoundland. The fact that it worked, and there's still some debate about whether that first signal was truly received, or whether Marconi heard what he wanted to hear in the static. But the fact that long-range radio worked at all was a puzzle. The answer turned out to involve something nobody knew about yet: the ionosphere. High above the Earth, starting maybe 80 kilometers up, there's a layer of the atmosphere where solar radiation strips electrons from gas molecules, creating a shell of electrically charged particles. And this ionized layer reflects radio waves back down toward the ground. So the signal doesn't have to travel in a straight line. It bounces off the ionosphere like a billiard ball off a cushion, skipping along between the ground and the sky, hopping around the curve of the Earth. The ionosphere acts as a waveguide, a natural channel that traps certain radio frequencies and lets them propagate enormous distances. This wasn't understood until the 1920s, when scientists like Edward Appleton confirmed the ionosphere's existence experimentally. But Marconi didn't need to understand why it worked. He just needed it to work. And that's a pattern you see over and over in engineering. The practical application sometimes races ahead of the theoretical understanding. People were building steam engines before thermodynamics was properly formulated. People were making steel before they fully understood metallurgy at the atomic level. And people were sending radio signals around the world before anyone could explain how those signals were bending around a curved planet. But here's the thing. I mentioned rival claims, and this is where the story gets tangled. Marconi gets the credit in most popular histories, and he won the Nobel Prize in Physics in 1909 for his contributions to wireless telegraphy. But there were others. Nikola Tesla, the Serbian-American inventor, had been lecturing about wireless communication and demonstrating radio frequency devices as early as 1893. Tesla filed key radio patents before Marconi did. In fact, the U.S. Patent Office initially rejected Marconi's patent application because it was too similar to Tesla's existing patents. Then, in a move that's still debated by historians, the Patent Office reversed itself in 1904 and awarded the patent to Marconi. Some people suspect this had to do with Marconi's powerful financial backers, including Andrew Carnegie and Thomas Edison. Tesla was furious. He sued. The case dragged on for decades, and in 1943, months after Tesla died, alone and broke, in a New York hotel room, the U.S. Supreme Court ruled that Tesla's patents had priority. But by then, nobody was paying attention. Marconi had the Nobel Prize, the fame, the legacy. Tesla had a Supreme Court ruling that came too late to matter, and Tesla wasn't the only one with a legitimate claim. In Russia, a physicist named Alexander Popov demonstrated a radio receiver in 1895, possibly before Marconi's earliest demonstrations. In India, Jagadish Chandra Bose was doing remarkable work with millimeter-wave radiation in the 1890s, building some of the first semiconductor detectors. The history of radio isn't a clean story of one inventor. It's a tangle of parallel discoveries, each building on Hertz's confirmation of Maxwell's prediction, each approaching the same technological frontier from a slightly different angle. But let's step back from the priority disputes for a moment, because there's something deeper happening here that's worth sitting with. What Maxwell's theory and Hertz's experiment revealed, and what radio made viscerally real to ordinary people, was that empty space isn't empty. It's full of fields, invisible, intangible, but absolutely real fields that carry energy and information across vast distances. You can't see them, you can't touch them, but they're there, passing through your body right now. Radio waves, television signals, cellular data, Wi-Fi, Bluetooth, GPS satellite signals, the cosmic microwave background left over from the Big Bang itself, all of it electromagnetic radiation. All of it governed by the same four equations that Maxwell wrote down and Heaviside polished. All of it the same fundamental phenomenon that Thales noticed when he rubbed amber 2,600 years ago, and William Gilbert puzzled over in his London study, just understood now at a level those early thinkers could never have imagined. And this brings us to something that was lurking inside Maxwell's equations from the very beginning, something that Maxwell himself noticed, but that nobody fully appreciated until a young patent clerk in Bern, Switzerland, started thinking very carefully about what it meant. Because Maxwell's equations don't just predict electromagnetic waves, They predict something specific about those waves. They always travel at the same speed. Always. Regardless of how fast the source is moving, regardless of how fast the observer is moving. The speed of light, according to Maxwell's equations, is a constant. It's baked into the fabric of electromagnetism itself, determined by those two fundamental constants, the permittivity and permeability of free space. And in the late 1800s, that created a problem, a serious problem, because it seemed to contradict everything physicists thought they knew about how velocities work. If you're on a train moving at 60 miles per hour and you throw a ball forward at 20 miles per hour, someone standing on the platform sees the ball moving at 80. Velocities add. That's basic Newtonian mechanics. But Maxwell's equations were saying that light doesn't work that way. Light always moves at the same speed, no matter what. And a young Albert Einstein, who had been fascinated by electromagnetism since he was a teenager, he later said he used to imagine what it would be like to ride alongside a beam of light, took that contradiction and refused to let it go. He didn't sweep it under the rug. He didn't assume Maxwell must have gotten something wrong. He did the opposite. He assumed Maxwell was exactly right, and that if something had to give, it was our everyday intuition about space and time. Now, Einstein in 1905 was 26 years old. He wasn't a professor. He wasn't at a prestigious university. He was working as a technical expert, third class, at the Swiss Patent Office in Bern, reviewing patent applications for electromagnetic devices. Actually, things like dynamos and signaling equipment, which is kind of perfect when you think about it. He was surrounded by the practical machinery of electromagnetism every single day, and in his spare hours, in the evenings and on weekends, he was wrestling with the deepest theoretical implications of the very same physics. He'd studied Maxwell's equations thoroughly as a student at the ETH in Zurich, and this puzzle about the speed of light had been gnawing at him for nearly a decade. Here's the thing that made Einstein different from a lot of other brilliant physicists of his era. Many of them saw the contradiction too. They knew that Maxwell's equations predicted a fixed speed of light, and they knew that clashed with Newtonian velocity addition. But most of them assumed the fix would come from modifying electromagnetism somehow, or from finding the special reference frame, the luminiferous ether, that hypothetical medium that light was supposed to wave through, relative to which Maxwell's speed was defined. The idea was that light traveled at its famous speed only relative to the ether, and if you moved through the ether, you'd measure a different speed, just like you'd expect from Newtonian mechanics. The ether saved the old rules. It was a comfortable assumption, except it didn't work. And this is where an experiment from 1887 comes in, one of the most famous null results in the history of science. Albert Michelson and Edward Morley, working in Cleveland, Ohio, built an incredibly precise interferometer to detect the Earth's motion through the ether. The logic was straightforward. The Earth orbits the Sun at about 30 kilometers per second. If the ether exists and is roughly stationary, then as the Earth plows through it, light traveling in the direction of Earth's motion should be slightly slower, like swimming upstream, and light traveling perpendicular to that motion should be slightly faster, relatively speaking. Michelson's interferometer split a beam of light into two perpendicular paths, bounced them off mirrors, and recombined them. If the two beams traveled at even slightly different speeds because of the ether wind, you'd see an interference pattern shift. The instrument was sensitive enough to detect differences far smaller than what the Earth's orbital speed should produce, and they found nothing, no shift, no ether wind. No matter which direction they aimed the apparatus, no matter what time of year they tested, the speed of light was the same in every direction. The ether if it existed, was completely undetectable. Michelson was actually disappointed. He considered the experiment a failure because it didn't find what he was looking for. But that null result was one of the most important measurements in physics. Now, some very clever physicists tried to rescue the ether. Hendrik Lorentz in the Netherlands and George Fitzgerald in Ireland independently proposed that objects moving through the ether physically contract in the direction of motion. That matter literally gets shorter when it moves, and this contraction would be exactly the right amount to cancel out the expected time difference in the Michelson-Morley experiment. Lorentz worked out the mathematics beautifully. He derived transformation equations, the Lorentz transformations, that described how measurements of space and time would change between reference frames moving relative to each other. These equations were mathematically correct. They perfectly preserved the form of Maxwell's equations, but Lorentz still thought of them as describing a mechanical effect, the ether squishing matter as it moved through. Einstein looked at the same mathematics and saw something completely different. And this is what makes his 1905 paper so revolutionary. He didn't start from the ether. He didn't start from mechanics. He started from two simple postulates, two assumptions, and derived everything else. The first postulate was the principle of relativity. The laws of physics are the same in all inertial reference frames. No experiment you can do in a smoothly moving laboratory will tell you that you're moving in any absolute sense. The second postulate was the one that came straight from Maxwell. The speed of light in a vacuum is the same for all observers, regardless of the motion of the source or the observer. That's it. Two postulates. And from those two ideas alone, Einstein showed that space and time themselves must be flexible. Time passes at different rates for observers moving relative to each other. Lengths contract. Events that are simultaneous for one observer aren't simultaneous for another. Mass and energy are related by that equation everyone knows, E equals mc squared, which also fell out of this same framework in a short follow-up paper later that year. Think about what happened here. Electromagnetism, this thing that started with Thales rubbing amber, that Gilbert cataloged, that Franklin theorized about, that Faraday visualized with his lines of force, that Maxwell unified into 4 equations. Electromagnetism forced a revolution in our understanding of space and time themselves. The speed of light isn't just some number that happens to describe how fast a particular phenomenon travels. It's a fundamental structural constant of the universe. It's the speed limit woven into the geometry of space-time. And we only discovered that because Maxwell's equations were stubborn. They refused to behave the way Newton's mechanics said they should. They insisted that the speed of light was always the same, and Einstein had the audacity to believe them. And here's what's really beautiful about this. Einstein's special relativity didn't overthrow Maxwell. It vindicated Maxwell. It showed that Maxwell's equations were more fundamental than Newton's laws of motion. When there's a conflict between electromagnetism and classical mechanics, it's classical mechanics that needs updating, not electromagnetism. The Lorentz transformations that Lorentz had derived as a kind of patch to save the ether, Einstein showed those were the actual rules of the universe. Space and time really do behave that way. It's not matter being squished by some invisible medium, it's the geometry of reality itself. So by 1905, electromagnetism had done something extraordinary. It had unified electricity, magnetism, and light into a single framework, predicted and confirmed the existence of radio waves, launched an entire telecommunications revolution, and then, almost as a side effect, forced humanity to completely rethink the nature of space and time. That's a lot of work for 4 equations. But the story doesn't stop there, because there was another revolution brewing, and electromagnetism was at the center of that one too. This second revolution was quantum mechanics, and it started, oddly enough, with a problem about hot objects glowing. You've seen this. Heat a piece of metal, a poker in a fire, say, and it starts to glow. First a dull red, then orange, then yellow, and if you get it hot enough, white and eventually bluish white. The color of the glow depends on the temperature. By the late 1800s, physicists were trying to calculate exactly how much radiation a hot object emits at each wavelength, and they had a problem. Classical electromagnetic theory, Maxwell's equations applied to the oscillating charges in a hot body, predicted that the amount of radiation should increase without limit as you go to shorter and shorter wavelengths. Ultraviolet, then beyond. The theory said a hot object should radiate infinite energy at the ultraviolet end of the spectrum. This was obviously wrong. Hot objects don't blast out infinite ultraviolet radiation, and the problem became known as the ultraviolet catastrophe. Beautiful name for a theoretical disaster. In 1900, Max Planck in Berlin found a mathematical fix, and it was a strange one. He proposed that the oscillating charges in a hot body couldn't emit or absorb energy in any arbitrary amount. Instead, energy came in discrete packets, quanta, with the energy of each quantum proportional to the frequency of the radiation. He introduced a new constant, now called Planck's constant, usually written as h, an incredibly tiny number. Planck himself wasn't entirely comfortable with this idea. He saw it as a mathematical trick, a way to make the equations work out. He spent years trying to find a way to get the same result without quantization. He couldn't. Then Einstein, the same Einstein, in the same miraculous year of 1905, took Planck's idea and ran with it in a direction that was even more radical. He proposed that it wasn't just the emission and absorption of light that was quantized. Light itself came in discrete packets of energy, particles of light. What we now call photons, though that name came later, coined by the chemist Gilbert Lewis in 1926. Einstein used this idea to explain the photoelectric effect, the observation that when you shine light on a metal surface, it can knock electrons loose, but only if the light's frequency is high enough. Brighter light of too low a frequency does nothing, no electrons. But even dim light of sufficiently high frequency kicks electrons out immediately. Classical wave theory couldn't explain this. If light were a continuous wave, then brighter light of any frequency should eventually deliver enough energy to liberate electrons. But Einstein's photon picture explained it perfectly. Each photon carries an energy proportional to its frequency. If a single photon doesn't carry enough energy to knock an electron free, then no number of those low-energy photons will do it either, because the interaction is one photon at a time. It was this work on the photoelectric effect, not relativity, that earned Einstein his Nobel Prize in 1921. And now something deeply strange had happened to electromagnetism. Maxwell had shown conclusively that light is a wave, an electromagnetic wave, with electric and magnetic fields oscillating in lockstep, spreading through space. Hertz had confirmed it experimentally. Interference, diffraction, polarization, all wave phenomena, all beautifully demonstrated. And now Einstein was saying, light is also a particle, a quantum, a discrete lump of energy. Both descriptions were correct. Both were necessary. Light behaves like a wave when you look at how it propagates, how it interferes, how it diffracts. And it behaves like a particle when you look at how it interacts with matter, how it's emitted and absorbed. This wave-particle duality, as it came to be called, was one of the great conceptual puzzles of early 20th century physics, and it eventually led to the full development of quantum mechanics in the 1920s, with Heisenberg, Schrödinger, Dirac, Born, and others building the mathematical framework that could handle this strange dual nature. And the quantum theory of electromagnetism, quantum electrodynamics, or QED, became the most precisely tested theory in the history of science. Richard Feynman, Julian Schwinger, and Shinichiro Tomonaga developed QED in the late 1940s, and it can predict certain quantities, like the magnetic moment of the electron, to more than 10 decimal places of accuracy. 10 decimal places. That's like predicting the distance from New York to Los Angeles to within the width of a human hair. It's almost absurdly precise, and QED is, at its heart, still electromagnetism. It's the quantum version of the same force that Thales noticed, that Faraday visualized, that Maxwell wrote down. It describes every interaction between light and matter, every photon absorbed by your retina when you see, every chemical bond holding molecules together, every signal traveling through every nerve in your body right now, the electric force between the electrons in your atoms and the protons in your nuclei, the force that gives matter its structure, its rigidity, its texture. That's all electromagnetism, described at the deepest level by QED. So from one force, one unified phenomenon, we got relativity and quantum mechanics, the two pillars of modern physics. Both of them grew directly out of puzzles that electromagnetism created. And the thing that ties them together, the thing that physicists are still working on today, is the question of gravity. Because gravity is the one fundamental force that doesn't fit neatly into the quantum framework. Electromagnetism, the strong nuclear force, the weak nuclear force. Those three have all been successfully described in quantum terms. They all have their own versions of QED, their own quantum field theories. But gravity, described so beautifully by Einstein's general relativity, resists quantization. It's been almost a century now, and the greatest minds in theoretical physics are still working on it. String theory, loop quantum gravity, various other approaches. They're all attempts to finish the job that Maxwell accidentally started, which is to unify all of nature's forces into one coherent picture. But let's not get lost in the far frontier. Let's come back to something closer, something you can feel. Because while the theorists were chasing unification, the engineers were doing something equally remarkable. They were taking electromagnetism, this force that had been a laboratory curiosity in Faraday's day, and they were weaving it into the fabric of civilization. And that story, the story of how electromagnetism became the invisible infrastructure of modern life, is worth sitting with for a moment. Think about what happened in the span of a single human lifetime. Someone born in 1840, the year Faraday was doing his most mature work, could have lived to see electric lighting, the telephone, radio broadcasting, the first television demonstrations, and the beginnings of radar. One lifetime. When that person was born, the fastest way to send a message across the Atlantic was to put it on a ship. By the time they died, voices were traveling through the air at the speed of light. That transformation, that total rewiring of human experience, was all electromagnetism. Every bit of it. And here's what's fascinating about the engineering side of the story. The theory came first, and then the applications followed. But the applications also pushed the theory forward. It wasn't a one-way street. Edison and his engineers, working on practical electric lighting in the 1870s and 1880s, ran into problems that demanded better understanding of resistance, of heat dissipation, of the behavior of materials under sustained current. The telephone engineers at Bell Labs, trying to send signals across longer and longer distances without degradation, ended up doing fundamental research in solid-state physics. The radar engineers of World War II, trying to generate and detect microwaves, developed the cavity magnetron and pushed microwave physics into entirely new territory. Practice and theory kept feeding each other, this beautiful loop where a practical problem would reveal a gap in understanding, and filling that gap would open up new practical possibilities. Let's talk about one thread that ties so much of this together: semiconductors. Because semiconductors are, in a very real sense, the culmination of everything we've been talking about. They're the place where quantum electromagnetism meets everyday life in the most direct possible way. Here's the basic idea. You've got conductors, metals like copper, where electrons flow easily. And you've got insulators, materials like glass or rubber, where electrons basically don't flow at all. Semiconductors are in between, materials like silicon and germanium. On their own, they're pretty poor conductors. But here's the thing, you can tune them. You can add tiny amounts of other elements, a process called doping, and dramatically change how they conduct electricity. Add a little phosphorus to silicon, and you get extra free electrons. That's called N-type, for negative. Add a little boron, and you create holes, places where an electron is missing, which behave almost like positive charge carriers. That's P-type. And when you put N-type and P-type silicon together, right next to each other, something remarkable happens at the junction. At that boundary, electrons from the N side drift over to fill holes on the P side, creating a thin region called the depletion zone, where there are very few free charge carriers. This depletion zone acts like a one-way valve. Current flows easily in one direction, from P to N, but is blocked in the other direction. That's a diode, the simplest semiconductor device. And it's pure electromagnetism at work, the behavior of charged particles in electric fields, governed by quantum mechanics, doing something useful. Now, the history here is wonderful. People had noticed strange one-way conduction effects in certain crystals as far back as the 1870s. Ferdinand Braun, the same Braun who improved Marconi's radio transmitters, demonstrated in 1874 that certain metal crystal contacts conducted current in only one direction. He didn't fully understand why. Nobody did, not for decades. The early radio engineers used crystal detectors, a thin wire touching a crystal of galena, which is lead sulfide, to pick up radio signals. They called the wire a cat's whisker, and finding the right spot on the crystal where it worked was genuinely an art. You'd sit there, gently probing different points on the crystal surface, trying to find a spot where the signal came through clearly. It was finicky and unreliable, but it worked, and nobody could fully explain why until quantum mechanics came along. It took until the late 1920s and 1930s for physicists like Felix Bloch, Alan Wilson, and others to develop the quantum theory of solids, band theory, which finally explained how semiconductors work. The idea is that in a crystalline solid, the allowed energy levels for electrons aren't just discrete levels like in a single atom. They spread out into bands, continuous ranges of allowed energies. In a conductor, the highest occupied band is only partially filled, so electrons can easily move to nearby empty states and carry current. In an insulator, the highest occupied band is completely full, and there's a large energy gap, the band gap, before the next available states. Electrons can't jump that gap under normal conditions, so no current flows. In a semiconductor, the band gap is small enough that thermal energy, or a little bit of doping, or an applied voltage, can push electrons across it. That's the whole secret. The band gap, a quantum mechanical property that determines whether a material is a conductor, an insulator, or that magical in-between thing. And once you understand the physics, you can engineer with it. The transistor, arguably the most important invention of the 20th century, came out of this understanding. At Bell Labs, in December 1947, John Bardeen and Walter Brattain demonstrated the first working transistor, a point-contact device made of germanium. Their colleague, William Shockley, who had been leading the semiconductor research group, soon developed the junction transistor, a more robust and manufacturable design. All three shared the 1956 Nobel Prize in Physics, and the transistor is, at its core, an electromagnetic device. It uses electric fields to control the flow of current through a semiconductor. A small signal at one terminal controls a much larger current between two other terminals. It's an amplifier. It's a switch. It's the building block of every computer, every smartphone, every digital system on Earth. Think about what that means. Maxwell's equations, which describe how electric and magnetic fields behave. Quantum mechanics, which explains how electrons behave in crystalline solids. Those two things together give you the transistor. And the transistor gives you, well, everything. The device you might have used to play this recording, the servers that stored it, the networks that delivered it, the satellites that help synchronize the timing. All transistors, all the way down, and the scale of it is staggering. A modern processor chip, something like the chip in a recent smartphone, contains something on the order of 15 billion transistors. Each one is just a few nanometers across, a few billionths of a meter. You could fit thousands of them across the width of a human hair, and every single one of those transistors is a tiny electromagnetic switch, turning on and off billions of times per second, manipulating electric fields at the quantum scale to process information. Faraday, who could barely do arithmetic, whose mathematical notation was so unconventional that it frustrated his contemporaries, he set in motion the chain of understanding that led to this, from his hand-wound coils and iron rings to 15 billion transistors on a chip the size of your fingernail. That's the arc. And it's not just computing. Semiconductors gave us LEDs, light-emitting diodes, which work by the reverse process of solar cells. In a solar cell, photons knock electrons across the band gap, generating current. In an LED, you push current across the junction, and when electrons fall back down across the band gap, they emit photons, light. The color of the light depends on the size of the band gap, which depends on the semiconductor material. Gallium arsenide gives you infrared. Gallium phosphide gives you green. And for decades, blue was the missing piece. Nobody could find a semiconductor system that efficiently emitted blue light. Without blue, you couldn't make white LEDs because white light requires mixing red, green, and blue. It took heroic work by Isamu Akasaki, Hiroshi Amano, and Shuji Nakamura, working with gallium nitride through the 1980s and 1990s to finally crack blue LEDs. They won the 2014 Nobel Prize for it. And now, white LEDs are everywhere. In your home, in streetlights, in flashlights, in screens. They use a fraction of the energy of incandescent bulbs. They last tens of thousands of hours. And they're pure applied electromagnetism. Electrons interacting with photons across a carefully engineered band gap. So here we are. We've followed this thread from Thales rubbing amber, through Gilbert's careful experiments, through Franklin's kite and Volta's pile and Ørsted's compass needle, through Faraday's rotating wire and his rings of iron, through Maxwell's equations and Hertz's sparks, through Einstein's relativity and Planck's quanta, through QED and semiconductors and transistors. And the remarkable thing, the thing that I keep coming back to, is that it's all one story. It's all one force. The static cling on your socks, the light from your lamp, the radio waves carrying music through the air, the magnetic field of the earth, the signals in your nerves, the structure of atoms, the colors of a sunset, all manifestations of the same underlying phenomenon. One force understood from different angles, at different scales, through different mathematical lenses. And there's something almost meditative about that unity, something calming about knowing that beneath the bewildering complexity of the modern world, there's this elegant framework holding everything together. One set of rules, discovered piece by piece over centuries, by people who were curious enough to look closely and brave enough to follow where the evidence led, even when it contradicted everything they thought they knew. And you know, that's worth sitting with for a moment, because it's easy to take electromagnetism for granted. You flip a switch, a light comes on. You tap a screen, information appears. You speak into a phone, and someone on the other side of the planet hears your voice. These things feel ordinary now. They feel like they've always been here. But every single one of them rests on this invisible architecture that took humanity thousands of years to even begin to understand, and really only about 200 years to work out in detail. 200 years. That's nothing. That's a few human lifetimes. Your great-great-great-grandmother might have been born into a world lit entirely by fire, and here you are, lying in a room illuminated by photons emitted from a semiconductor junction engineered at the atomic scale. The gap between those two realities is electromagnetism, understood and harnessed. And what strikes me, thinking about it now, is how the story never really ends. It keeps going. Because even though we've traced this beautiful arc from ancient amber all the way to quantum electrodynamics and billion transistor chips, the frontier is still moving. People are still discovering new things to do with this one force, still finding new ways to coax electrons and photons into doing remarkable things. Take quantum computing, for instance. Here's the thing about classical computers, the ones we've been talking about, built from transistors. They process information as bits, zeros and ones. A transistor is either on or off. And that's incredibly powerful, obviously. It got us to where we are. But there are certain kinds of problems, certain calculations, that are so complex, so combinatorially explosive, that even a classical computer with billions of transistors would take longer than the age of the universe to solve them. And that's where quantum computing enters the picture. Instead of bits, you work with qubits, quantum bits, which exploit the quantum mechanical properties of electromagnetic systems to exist in superpositions of states. A qubit can be 0, 1, or a quantum combination of both simultaneously. And when you entangle multiple qubits together, the computational space grows exponentially. 2 qubits don't give you twice the power of 1. They give you 4 times. 3 qubits give you 8 times. 50 qubits give you more simultaneous states than there are atoms in a typical human body. Now, building a working quantum computer is extraordinarily difficult. The quantum states are fragile. They decohere, they lose their quantumness almost instantly when they interact with their environment. So you have to isolate them, cool them to temperatures colder than outer space. shield them from stray electromagnetic fields. It's one of the hardest engineering challenges humans have ever attempted. But at its core, it's still electromagnetism. The qubits in many leading designs are superconducting circuits, tiny loops of metal cooled to near absolute zero, where electrical resistance vanishes and current flows without dissipation, and the electromagnetic energy in the circuit becomes quantized into discrete levels that you can manipulate as quantum information. Other designs use trapped ions, individual atoms suspended in electromagnetic fields, their quantum states controlled by precisely tuned laser pulses. Photons of specific frequencies interacting with electrons in specific energy levels. It's Faraday and Maxwell and Planck and Feynman, all woven together into something that would have seemed like pure magic to any of them individually, yet follows directly from the principles they uncovered. And then there's the way electromagnetism is reshaping energy. Solar cells, which we touched on, photovoltaic technology, are getting cheaper and more efficient every year. The basic physics hasn't changed since Einstein explained the photoelectric effect in 1905. Photons come in, electrons get knocked loose, current flows. But the engineering keeps advancing. Multi-junction cells that stack different semiconductor materials to capture different wavelengths of sunlight. Perovskite solar cells, made from a class of crystalline materials that can be deposited as thin films, potentially much cheaper to manufacture than traditional silicon. Tandem cells that combine perovskites with silicon to push efficiencies above 30%. All of it electromagnetic engineering at the quantum level, tuning band gaps, managing photon absorption, optimizing electron transport. Or think about wireless power transfer, something that would have delighted Tesla enormously. We're actually doing it now, in limited ways. The wireless charging pad for your phone works through electromagnetic induction, the same principle Faraday discovered in 1831. A coil in the pad carries alternating current, which creates a changing magnetic field, which induces a current in a coil inside your phone. It's Faraday's iron ring, miniaturized and refined, sitting on your nightstand. And researchers are working on longer-range wireless power, using resonant coupling, where two electromagnetic systems tuned to the same frequency can exchange energy efficiently even across a gap. It's not science fiction. It's Maxwell's equations, applied with modern precision. And here's something that I find quietly beautiful. The electromagnetic spectrum, this vast continuum of waves that Maxwell's equations predicted. We keep finding new uses for it. Radio waves carry your Wi-Fi and your Bluetooth and your cell signals. Microwaves heat your food and relay satellite communications. Infrared lets your TV remote work and lets thermal cameras see in the dark. Visible light, that tiny sliver of the spectrum, is what your eyes evolved to detect, and it's also what carries data through fiber optic cables. Pulses of laser light, bouncing along glass fibers thinner than a human hair, carrying virtually all of the world's internet traffic. Ultraviolet light sterilizes water and medical equipment. X-rays let doctors see your bones. Gamma rays treat cancer. Every single one of these is the same thing, the same phenomenon. Oscillating electric and magnetic fields, differing only in frequency and wavelength. The whole vast infrastructure of modern communication, medicine, cooking, imaging, sensing, it's all riding on Maxwell's waves. And the thing about fiber optics, actually, is worth pausing on, because it's such a perfect example of how deeply electromagnetism is woven into things you never think about. When you stream a video, or send a message, or make a video call, that data almost certainly travels through optical fiber for most of its journey. And the way it works is pure applied electromagnetism. A laser, which itself is a quantum electromagnetic device using stimulated emission of photons, the process Einstein first described theoretically in 1917, a laser generates coherent light at a specific wavelength. That light is modulated, switched on and off billions of times per second to encode digital information. Then it's sent into a glass fiber, where it bounces along by total internal reflection, the light trapped inside the glass core, by the difference in refractive index between the core and the cladding. And it can travel for kilometers before the signal needs to be amplified. The amplifiers themselves are electromagnetic, erbium-doped fiber amplifiers that use the quantum energy levels of erbium atoms to boost the optical signal without converting it to electricity first. The whole system, from laser to fiber to amplifier to detector, is electromagnetism from end to end. And it carries something like 95% of all intercontinental data traffic. Every time you access a website hosted on another continent, your request and the response are traveling as pulses of light through cables on the ocean floor. Cables that cross the Atlantic, the Pacific, thread through the Mediterranean, loop around Africa. There are over 1 million kilometers of submarine fiber optic cable on the Earth right now. And it's all light, all photons, all Maxwell. So when I say the story never ends, that's what I mean. The fundamental physics was largely in place by the mid-20th century. QED gave us the most precise theory in the history of science. But the engineering, the creative application of these principles, that's still accelerating. Every year, someone figures out a new way to use the electromagnetic force to do something useful, or beautiful, or both, and maybe that's a good place to let the story come to rest. Not because it's over. It's not. It won't be for a very long time, but because we've followed it far enough to see the shape of it. And the shape is remarkable. It starts with wonder. Thales, 2,600 years ago, rubbing amber and watching bits of straw leap toward it. He didn't know why. He just noticed, and noticing, paying attention to something small and strange, that's where it all begins. Then, centuries of slow accumulation. William Gilbert, methodically testing materials, separating electricity from magnetism, insisting on experiment over speculation. Benjamin Franklin, flying his kite, unifying lightning with the spark from a Leyden jar. Galvani and Volta, arguing about frogs, and in the process, giving us the battery. Each step building on the last, each discovery opening a door that nobody knew was there. Then the great unifiers. Ørsted, noticing his compass needle twitch near a current-carrying wire, and in that single moment, revealing that electricity and magnetism were connected. Faraday, with almost no formal education, imagining invisible lines of force filling space, building the first motor, discovering induction, giving us the conceptual framework that would become field theory. Maxwell, translating Faraday's intuitions into mathematics, predicting electromagnetic waves, revealing that light itself was electromagnetic. 3 people, working across about 50 years, who fundamentally changed humanity's understanding of the universe. Then the validators and the appliers. Hertz, generating and detecting radio waves in a laboratory, confirming Maxwell's prediction. Marconi and Tesla and all the others, turning those waves into communication. Edison and Westinghouse and Tesla again, electrifying the world, each one taking the pure understanding and turning it into something that changed daily life. Then the revolutionaries. Planck, reluctantly introducing the quantum. Einstein, reimagining space and time, showing that electromagnetism demanded relativity. Bohr, Heisenberg, Schrödinger, Dirac, building quantum mechanics. Feynman, Schwinger, Tominaga, perfecting QED. Each generation going deeper, finding more precise and more beautiful descriptions of the same force that Thales first encountered as a mysterious attraction in a piece of amber. And then the engineers of the quantum age, Bardeen, Brattain, and Shockley, inventing the transistor, Kilby and Noyce creating the integrated circuit, Akasaki, Amano, and Nakamura cracking the blue LED. Thousands of others, physicists, chemists, materials scientists, electrical engineers, turning quantum electromagnetism into the technology that defines modern life. It's all one thread, one continuous thread, stretching from the ancient Mediterranean to the lab bench to the factory floor, to the device you might be holding right now, or the one sitting on your nightstand, or the lights in your ceiling, or the signals passing invisibly through the air around you at this very moment. Electromagnetic waves, carrying information, carrying energy, carrying music and voices and images, passing right through you as you lie there, as gentle and as pervasive as the air you're breathing. And here's the last thing I want to leave you with, and it's simple. All of this vast, intricate, world-transforming understanding came from people who were paying attention, people who noticed something odd and didn't let it go, a compass needle deflecting, a frog's leg twitching, a spark jumping a gap, a mathematical equation that had an unexpected symmetry. They paid attention, they asked why, and they followed the thread wherever it led. And the thread led here, to a world held together, connected, illuminated, and animated by a single force that we now understand with breathtaking precision. So as you lie there, feeling the warmth of your blankets, in a room that might be gently lit or comfortably dark, know that the electromagnetic force is everywhere around you and within you. The electrons in your atoms are bound to their nuclei by it. The chemical bonds in your body are shaped by it. The nerve signals carrying your thoughts are electromagnetic pulses. The warmth you feel is infrared radiation, electromagnetic waves emitted by everything around you. You are, in a very real sense, an electromagnetic being, lying in an electromagnetic world. And the fact that we understand this, that we figured it out, piece by piece, century by century, through curiosity and persistence and the occasional flash of genius, that's one of the most remarkable things our species has ever done. So rest easy with that. Let the story settle. Let the names and the dates and the equations fade into the background, and just hold on to the feeling of it, the quiet wonder that the universe is comprehensible, that it plays by rules we can discover, and that something as simple as rubbing a piece of amber could lead, eventually, to everything. That's electromagnetism. That's the story. And now, you can sleep.